Okay, so 3.2 day 1, we're talking about differentiability today, more specifically. We kind of started on it yesterday. I tried to sneak a little bit of 3.2 day 1 into 3.1 day 2, and there's a little bit of tomorrow snuck in here too. So that way we're kind of overlapping our lessons a bit. This is kind of a challenging exercise. I've got here a function, and I'd like you to try and graph or sketch the derivative of it. What do you suppose the derivative would look like? So, why don't you guys take a few minutes? I'll just set a timer, and you can try it out. See if you can sketch. You can draw it right on top of this. So just draw this, and then draw the derivative right on the same graph. There was the answer. This is something I'll post on Edmodo, but it's basically a definition from that Master Math Mentor guy. You guys remember when you did the Are You Ready for Calculus thing? Yeah, he has some really good stuff. But he basically has definition for differentiability at a point, differentiability for an interval, and differentiability for a function in general. All right. Let's ask a different question about this. You guys remember on my test I had you guys answering where you thought the graph was continuous? Well, let's ask now where you think the graph is differentiable. Okay, this is a classic AP question. So, where is it differentiable? I'll give you a few minutes to look at that and write down what you think. It's the same graph you had a minute ago. First of all, it's differentiable wherever you can draw a tangent line that actually has a slope. So I could draw a tangent line for any part of this parabola, no problem. But when I get to x equals 1, I have some difficulty drawing a tangent line. Right? Okay, so far this is what I'm concluding. I believe I can draw a tangent line anywhere from negative infinity all the way to 1. But at 1, I have some trouble drawing a tangent line. I don't know how to draw that. Okay. Once I get on to this second piece, I can draw a tangent line for any point on here. No sweat. So basically, from 1 to 3, things seem differentiable. 3 isn't even continuous, so I'm not going to include that. And then, from 3 to 4, I can draw tangent lines. So the answer is from negative infinity to 1, or from 1 to 3, or from 3 to 4. These are all domains, intervals that are differentiable. What about continuous but not differentiable? All right, so I need to move my answer. So that was called moving the question. Let's move this down here. All right. What about continuous but not differentiable? Anyone think they know? X equals 1. Okay, yeah, this is actually all we got. Because x equals 1 is the only point on this graph where you would say things are differentiable, or continuous, but we can't seem to draw a tangent line there. Good. Good job. Okay, and then C might actually be the easiest thing to answer, because if it is not continuous, it is automatically not differentiable. Okay, you might as well put in the word therefore here, because we said yesterday, if a graph is not continuous, of course it's not differentiable. Okay, so let's just find the discontinuities. That's all it's asking for. Well, where are my discontinuities? X equals 3. And also any x is greater than 4, right? Because there is no graph after 3, or after 4 I mean. So you have to include that as non-continuous part of the graph. The graph doesn't continue over there. And then, of course, this arrowhead here means that the graph actually does keep going, right? So we don't have a...
What's the notation for like including and not including?
Okay, so if we want to include a point, let's say you want to include 4 for some reason, you would use a square bracket. Mm-hmm.
Do you not
Yeah.
include infinity just because it's like...
You can never include infinity because you can never attain it. Yes, question?
Do you not include 4?
I would include 4 as a continuous endpoint.
But not different?
I would...
in our textbook, a closed endpoint where the tangent lines have been arriving at a slope of 0 would be considered differentiable. So the endpoint here is considered differentiable at 4. Okay? So this is one of the reasons why Schwartz felt like he needed to put down 3 definitions for differentiability. He actually talks about differentiability at an endpoint. So I'll post it online. But just understand that endpoints are actually something that great minds disagree on. So we're not going to be too picky. But in our textbook, a closed endpoint is both continuous and differentiable, as long as you can draw a nice tangent line there and it appears to have a slope like 0 or 5 or something. 2/5. Okay? All right, I want to make 2 slight changes to this graph. The first one I already did earlier. I just simply closed this point. How does that affect our answer? It didn't affect the derivative graph, but it affects our answer in a bit here. I think we just got another answer for part B. You see? So what did I just do? In case you missed it, if you weren't watching, I filled in this point again because I want to talk about how that affects us on the answer. Is it still safe to say that at x equals 3 it is not continuous? We can't say that anymore, right? So this is no longer here. It is now one of those points where it is continuous but not differentiable. So that answer would jump to here, see? Okay, that's the first minor change I wanted to try. Here's a little bit more significant change. Instead of filling that point, what I'd like to do is reshape this piece. This is now the bottom right quarter of an ellipse. So forget this. This is now the bottom right quarter of an ellipse. So the ellipse would look like that. If I could draw the whole thing for you. How does that affect our answer? Or does it? Okay, you think it affects everything?
Oh, no. Oh, I was at, oh, no.
Well, how
I
does
did
it?
phrase that really wrong. I meant to ask, are you asking if it affects, like, the graph of the differential?
No, this actually would affect the graph.
Instead of horizontal, it would be like vertical.
Yeah, the second piece in the derivative would look different now. But I'm actually asking about these 3 and how we would change our answer now that that's no longer that straight line. Let me ask you this. If you were on a roller coaster and you got to the point at x equals 3, right here, would it be a smooth ride through?
Yes.
Yes, it would. Be a nice smooth ride right through here because you're going up. It's kind of like Superman, you know, you're going up that big ramp. And then you get to here and then you're just going onto this track. But there's no actual like sharp turn there, right? This was going steeper and steeper and steeper, and then it went shallower. So nice and steep maybe, but maybe you've seen things like this in advanced skate park. They used to have this huge half pipe, 13 feet tall, and at the top they had a rolling channel. So it goes up like this, and then there's an extension piece that goes up like that. Kids would roll off the top and go straight in. But this spot right here is truly vertical, right here, truly straight up and down. It's getting a little bit tougher now because if we say that this is differentiable, that means we can draw a line there, a tangent line there, which is true. The only problem with this tangent line is it's completely vertical. So what's its slope? Undefined. So yesterday, my definition of differentiability at the introductory level was the roller coaster analogy, that when you pass through a smooth point on a roller coaster, it is differentiable. There is an exception to that, and that is these vertical spots. So every time you go through a loop on a roller coaster, you actually hit 2 non-differentiable points. They are right here and right here. When you're going up and you're about to loop back over, as soon as you hit vert, straight up, at that instant, that's non-differentiable. It's not because it's not a smooth ride, it's because you have no slope there. And then when you come back around, you come back through the loop on your way down, when you hit that vertical tangent case, you lose your slope for that instant. Okay, so this is a subtle point, but what happened was the x equals 3 is now not differentiable, but continuous. See? It is continuous, but it is not differentiable there because of a vertical tangency. And this is a very subtle point, but it's very important. All right, so out with the definition, smooth ride on a roller coaster. In with the definition, a tangent line must be able to be drawn, and it must have a value for a slope. Okay? Yes?
How would that change the differentiable graph?
The derivative graph? It creates a vertical asymptote right there. Yeah. It already had one, but the left and end pieces both have an infinity slope. So basically, between what's going on, I'll go over it real quick. The tangent lines in this region are going from 0 to steeper, 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 and ultimately to infinity. So this piece of the graph is now going to go like this for the derivative graph. The slopes just went from 0 to infinity, and it happened all between x equals 1 and x equals 3. The right piece, remember, looked like this. Remember? So, does that help? Thanks for asking. Okay. So there are basically 4 ways to think of, or to recognize non-differentiable points. Okay, let me just run through them real quick. The book does this too. I like it. So, if you see a graph that has a sharp change in slope, like this one, you would say not differentiable at x equals 0. Okay? If your graph comes in like this and comes out like this, we call this point a cusp, and this is also not differentiable at that point. So I'm talking about x equals 0 here. Okay, if you see this, this is brand new. If a graph does this, and the tangent line can be drawn, but the tangent line doesn't have a slope because it's vertical, that also is non-differentiable. And the last case is the obvious case, if the derivative graph, if the function graph is simply broken, even slightly, even a hole, you're going to have no differentiability. A hole, a jump discontinuity, an oscillating discontinuity, any of those discontinuities we studied, if the graph has it, the derivative will not exist there. Okay, so let's just go through these 4 cases and we'll write down why f is not differentiable at 0. Okay? It's for 4 different reasons. Okay, so f is not differentiable at 0 because why? Because the LHD and the RHD are not the same. Here the LHD is -1. Let's assume this is the absolute value function. So LHD is -1, but the RHD is +1. We're talking about the slopes of the tangent lines are approaching -1 and +1 from either side of the origin. Abrupt change in slope. On this next one, it's almost the same idea. These slopes are getting closer to -infinity, but coming out of the right side, they are basically starting at infinity and decreasing. So we would say that f is not differentiable at 0 in the first case, it was because -1 is not equal to 1, but in this case, it's because -infinity is not the same as +infinity, see? Okay, these two are very, very similar. They're both because the LHD doesn't match the RHD. Okay, this is called a corner, and this is called a cusp. It's the only difference is one of them is 2 non-equal numbers, and the other is, one of these is like an infinity case, but they're not the same direction. Okay, this third one is f is not differentiable at x equals 0. Why? Because a tangent line can be drawn, but it doesn't have a slope. Okay, so a tangent line can be drawn, but it has no slope. And the last one is f is not differentiable at x equals 0 because, why? F isn't even continuous. Right. F is not continuous at x equals 0. And continuity is a prerequisite for differentiability, remember? Okay. 4 different cases. Any questions on those? So the AP test might have something multiple choice style that would say something like, which of these has a non-differentiable point at 0? And the answer is all of them. For one reason or another, do not have a tangent line at 0. Or if it does, you can't find its slope well. Okay, this is a really weird problem, but it is in your homework. One's like this. And they want us to show that this function is not differentiable at 0. Okay, so this is going to feel a little bit weird, because if you try to sketch this thing, you realize it's not even continuous at 0. I don't like that line. I'm not drawing that line. Go away. I don't like you. I want this kind of line. Okay, so I don't like that either. There we go. Oh, don't do that. All right. Let's draw this line. All right. If you try to graph this function, it's basically y equals 0 for all x's to the left of 0. It's kind of a weird function. And then if you get to 1, if you get to x equals 0, everything thereafter is at 1. So it looks like this. This is y equals 1, this is y equals 0. 2 pieces. You could have sketched that pretty easily. If I told you, hey, this is not differentiable at this origin, you'd be like, yeah, I know, it's not even continuous. There's a jump discontinuity, of course it's not differentiable. But we can still calculate LHD and RHD. Okay? So there's 2 reasons why we would say that f is not differentiable. F is not differentiable at x equals 0 because f is not continuous at x equals 0. And there's another reason why we would say it's not differentiable. LHD does not technically match RHD. Watch this. I'm going to try to show that LHD and RHD are not the same. All right, so LHD means this. Limo left, f of 0 plus h minus f of 0 all over h. RHD means limo plus f of 0 plus h minus f of 0 all over h. So remember, LHD and RHD are exactly the same thing except for the limit. Okay. Now, if h is a negative number, like in the case of limo minus, right? 0 plus h would mean a negative value, right? Because think about it, if this is negative 0.00000001, this is 0 plus negative 0.00000001. So this is left piece. For LHD, we're going to use the left piece here. So what is the left piece? Look at the graph. What happens if you plug 0 plus h into this part of the function? What are you going to get for y? 0. Everything's 0 on the left. So this is just 0. Not very helpful. What is f of 0? Be careful. Look at the picture. It's technically 1. And it's on the right piece. Interesting. So there it is. You asked about this earlier. Okay? All right, and then let's look at limo plus, and then we'll work these limits out. If h is a slightly positive number, say 0.01, 0 plus h would be a positive So we're actually looking over on the right side, and the graph there is 1. And everything up there is 1. So this is just uno, no matter what you put in for h. Y is always 1. So this is going to be limo plus, and this is just 1 minus f of 0. Well, what's f of 0? You can tell from the picture. What's f of 0? 1. Okay. So I was trying to show that these were not equal, and I did, because this comes out to limo minus of negative 1 over h, and this comes out to limo plus of 0. Let's do the right side first. What's limo plus of 0? 0, right? What is limo, careful, what is limo negative, or limo minus, of negative 1 over h? Imagine taking negative 1, but we're coming from the left. There's a specific something that's happening. If you plug in negative 0.1, or negative 0.01, or negative 0.001, what's happening? 10, 100, 1,000. What's happening? It's going to infinity. It's going to infinity. 1 over h, or I'm sorry, negative 1 over small negatives is going to produce an infinitely large answer. So what happened? Like, what's going on here? Well, we said it wasn't differentiable because the graph was broken. We can also see that we have a different LHD and RHD. Let me just draw a picture of why this happened, just real quick. So the left side looked like this, and the right side looked like this, and we were trying to connect a point here to a point here and find the slope. And we kept moving this point inward, but see how the slope is increasing? See that? If you pick that 0 point and you pick a point on the left, that line is getting steeper and steeper and steeper. It's going to infinity. But if you do that on the right side, if you pick the 0 and a point on the right, the secant line always has slope 0 no matter where you draw it. So you might have to do this on your homework. Just follow your notes.